AWSAlgorithmorModel Description: a model used to make predictions on data. It is a representation of the underlying patterns and relationships within data, allowing for insights and predictions about future events. Prerequisites: data availability. The model needs a sufficient amount of relevant data for training in. Evaluation: this data should be clean, organized, and in a format that can be easily processed by the chosen machine learning algorithm. Model training resources. Training a machine learning model requires computational resources, such as CPUs, GPUs, and memory. AWS provides various services like Amazon EC2, Amazon SageMaker, and Amazon Elastic Compute Cloud, Amazon ECS to fulfill these requirements. Use cases: predictive maintenance, predicting the likelihood of equipment failure and scheduling. Preventative maintenance based on historical data and real-time sensor readings. Fraud detection, identifying fraudulent transactions or activities by analyzing user behavior, payment patterns, and other relevant data. Customer churn prediction, predicting which customers are likely to leave a service based on their usage patterns, demographics, and other factors. Recommendation systems, suggesting products or services based on user preferences, past purchases, and browsing history. Image and object recognition, identifying objects and scenes in images and videos. Used in applications like self-driving cars, security systems, and medical imaging. Natural language processing, understanding and processing human language. Used in applications like chatbots, sentiment analysis, and machine translation. Steps: define model objectives. Clearly define the problem you want to solve and the desired outcome of the model. This includes specifying the target variable, the type of prediction, classification, regression, etc., and the evaluation metrics. Prepare and clean data. Data preprocessing involves cleaning, transforming, and organizing data to ensure its quality and suitability for training a model. This includes handling missing values, outliers, and categorical features, and transforming data into a format compatible with the chosen machine learning algorithm. Train model. Select an appropriate machine learning algorithm, e.g., linear regression, decision tree, neural network based on the problem and data characteristics. Train the model using the prepared data and adjust hyperparameters to optimize performance. Evaluate model performance. Assess the model's accuracy, precision, recall, and other relevant metrics using different evaluation techniques, e.g., cross-validation, holdout sets. This helps identify any bias or limitations and inform further model improvements. Deploy model. Deploy the trained model to a production environment where it can be used to make predictions on new data. This involves setting up infrastructure for model serving, managing API endpoints, and ensuring scalability and reliability. Challenges and fixes: data quality issues. Inaccurate, incomplete, or inconsistent data can significantly impact model performance. Data cleaning and preprocessing. This involves handling missing values, outliers, and inconsistent data entries. Techniques like imputation, normalization, and outlier detection can be used to address these issues. Data augmentation. Creating synthetic data based on existing data can help address data scarcity and improve model robustness. Model overfitting. When a model learns the training data too well and performs poorly on unseen data. Regularization techniques. These techniques, e.g., L1 and L2 regularization, penalize complex models and encourage simpler solutions. Reducing overfitting. Cross-validation. Dividing the data into multiple folds and training the model on different combinations of folds. evaluating its performance on the remaining fold, and averaging the results to get a more reliable estimate of its performance on unseen data. Model interpretability: difficulty in understanding the decision-making process of a model. Feature importance analysis: understanding the contribution of different features to the model's predictions. Model visualization: creating visual representations of the model's decision boundaries and feature interactions to gain insights into its behavior. Explainable AI techniques that aim to make complex models more transparent and understandable. Model drift: the performance of a model degrades over time due to changes in the data distribution or underlying patterns. Model monitoring and retraining: regularly monitoring the model's performance on new data and retraining it periodically to adapt to changes in the data. Adaptive learning algorithms: algorithms that can continuously learn from new data and update their parameters automatically without requiring explicit retraining. Ensemble methods: combining multiple models to improve robustness and reduce the impact of drift. Model deployment challenges: deploying a trained model in a production environment often involves complex infrastructure and operational considerations. Use of cloud-based machine learning platforms: AWS provides services like Amazon SageMaker and Amazon Machine Learning that simplify model deployment and management. Containerization and orchestration: using Docker containers to package the model and its dependencies, making it easier to deploy and manage across different environments. API endpoints: exposing the model as an API endpoint that can be accessed by other applications or services. Scalability and reliability: ensuring the model can handle large volumes of requests and is resilient to failures. Security: protecting the model and data from unauthorized access and malicious attacks.